My name is Jeremy McCulloch, and I will be talking about Gaussian constitutive neural networks. Previous methods for discovering constitutive models for biological and surgical materials predict the mean stress in a material as a function of the strain. However, if you look at real data, there's often lots of variation in the stress response between different samples. As a result, there's a need to build a method that predicts the probability distribution of stress across samples. There are some existing Bayesian methods that do exactly this, but they require an arbitrary prior to be selected for the material parameters, and this is often not known in practice. To address this, I developed a Gaussian constitutive neural network, which has a particular architecture that ensures that physical constraints are automatically satisfied. The final set of weights in this neural network are then modeled as multivariate Gaussian random variables with a learned mean and covariance matrix. Using probability theory, we can analytically compute the mean and variance of the stress for a given input strain. Then to train the model, we minimize the negative log likelihood, or NLL, of the data under the model distribution and introduce LP regularization to promote sparsity. When trained on experimental data from synthetic hernia meshes tested in biaxial tension, we can see that the model accurately predicts the data distribution. The model performs well not only in the training set, but also on a test set that was not used for training. The model we discover is an interpretable 4-term model with correlated weights. These results are useful because these stochastic constitutive models can be used to quantify uncertainty in downstream simulations, such as finite element models of surgical interventions or of disease progression.